Hey guys, welcome to our Chapter 5, Probability Distributions and the Binomial Distribution. Okay, this lecture is going to be a little different. Sorry about that. Just in the fact that I'm going to switch out of this slide and into a virtual calculator to kind of show you guys how to do some of these calculations, so that way we aren't getting confusion and getting tripped up on our calculators. They're very helpful for basically everything we're doing from here on out. So it's going to be kind of a normal be popping in and out of this. There's also a website listed under Chapter 5 that kind of has some step-by-steps on how to use your calculator for what we're going to use it for today. So let's get started. The key concept of what we're going to be talking about in this first part is random variables and probability distributions. We'll mention probability histograms, but that's kind of all we're going to do with them, is mention them. We'll talk about how to find mean, standard deviation, variances, just the square of the standard deviation, and then how to determine whether outcomes are significant or not. The biggest thing is our random variables and probability distribution. That's going to be the big takeaway. So what is a random variable? Well, very simply, a random variable is a variable that we represent by a lowercase x representing kind of a singular value, or sometimes we'll use an uppercase x to represent kind of all possible values of that random variable. So you may see kind of both things happening and stuff like that. It's just something that has a single numerical value determined by chance for each outcome of some procedure. Okay, that procedure could be flipping a coin. Procedure could be spinning a spinner, rolling a die. It could be all sorts of things. It could be talking to people, getting answers from questions and things like that. Now, when I say numerical, right, you flip a coin and we think, well, how is that a single numerical value? Just heads, tails isn't a numerical value, and so the heads and tails wouldn't be a random variable. But saying the number of heads we get, that would be a random variable because we either get one head or no heads on the first flip. We've gotten 0, 1, or 2 by the second flip, and so forth. And so that is a random variable. Now, just like data, there are two different types of random variables, and they have the same classifications. A discrete random variable is a collection of values that is finite or countable. Okay, so if there's infinitely many values, so we say that something is countable. Okay, if you can kind of individually number them, if you would. Right now, that would go on forever, but you could do it. So things just like discrete data, right? It's kind of got jumps, right? So like the number of things. So the number of, the example here is the number of tosses of a coin is a discrete random variable. Now, theoretically, for this example here, before getting ahead, you could flip the coin infinitely long and never get ahead. Theoretically, right? We know practically it's going to happen eventually. And so the variable there's no limit to the number of flips you could do. But there's 1 or 2 or 3 or 4, and so that is a countable set of countably infinite is what we call it. A continuous random variable is simply an infinite collection of values that is not countable. So if it's not a discrete random variable, it is then a continuous random variable. Since all of our random variables are numbers, we don't have any sort of qualitative or categorical type variables. Now, a probability distribution, this is something that gives the probability of each value of the random variable. Well, for smaller probability distribution situation or for smaller random variables, we'll use tables or sometimes a graph with a histogram. For larger ones, formulas work best. Now, formulas are defined, let's just say something like y equals x, okay? That goes infinitely far, right? There's infinitely many values, it's continuous, but we can use a formula to work even for a discrete random variable simply by saying basically like, oh, you only use this equation for these inputs, and those inputs would represent our random variable. So there's conditions for something to be a probability distribution. You can't just have a table out there and be like, boom, probability distribution. So there are 3 different conditions for a probability distribution. The first of which is that there is a numerical random variable and its number values are associated with corresponding probabilities. Okay, so thinking coin tosses, right? If I flip a coin twice, record the number of heads, that is a numerical random variable, and each number value, so getting no heads, 1 head, 2 heads, is associated with some corresponding probability. Okay. The next condition is that if we add all the probabilities up, that funny little symbol, this guy here, it's sigma is what it's called. Okay. Sigma P of x. So if we add all the probabilities together, it has to equal 1 or extremely close to 1. And when we say extremely close, what we mean is things like 0.99, 1.00, right? Things that happen by simply having little minor rounding errors, those are acceptable. So if we have, data values, let's say 3 different outcomes, each one has a probability of 1/3. So that's 0.333. We add that up 3 times, we get 0.999. Now, if we add 1/3 together 3 times, we get 1. And so that just happened from rounding 0.3 that repeats forever to 0.333. Okay, so don't be concerned if you add your probabilities up and get something less than 1 or a little greater than 1, most likely just because we're rounding. Now, if you get 1.5, 2, 3, that's a problem. And the last condition is that every probability value has to be between 0 and 1, which you're like going, well, yeah, that's what it means for something to be a probability, because probability values have to be between 0 and 1. But these probability distributions, especially if it's, say, a function, you could have something that adds up to 1, but if one of those probabilities isn't between 0 and 1, it doesn't work, right? I mean, if we just simply think of, say, one of the probabilities is 2, the other one is -1, we add those together, we get 1. So that meets the second condition, but obviously you can't have a probability of something happening being 2, and you can't have the probability of something happening being -1, so it doesn't work. Now, let's look at an example. I've talked about this, toss in a coin twice and recording the number of heads. So let's look at a probability distribution or a table of these values, and we'll say a potential probability distribution. So we look at our table here. We have on the left-hand column the number of heads we get when 2 coins are tossed, and on the right-hand column, the corresponding probabilities. Now notice, we're tossing 2 coins, but we have 3 possible outcomes. And the reason why is because there's 3 different things 3 different amounts of heads that we can get. It's not necessarily that we can get a head or we can't get a head, right? But it's that we can get no heads on the 2 flips, we can get 1 head on the 2 flips, and we can get 2 heads on the 2 flips. So if you're concerned about how to calculate those probabilities, right, this is a pretty simple one. I hope this isn't an issue for you. If it is an issue for you, you need to kind of, wouldn't be bad to refresh chapter 4. Think about that, right? Look at the sample space for the event space for flipping 2 coins, and it should be pretty clear where these probabilities come from. So with these, let's look and see if this meets our 3 conditions. So the variable x is a numeric random variable. It's the number of heads we get, and each one of those is associated with a probability. Cool. Condition 1, check. Condition 2, we can see here, we can see the work done. We have 0.25 is the probability of getting no heads, 0.5 the probability of getting 1, and 0.25 is getting the probability of 2 heads. We add those together, we get 1. Check. Condition 2. Now, condition 3 is just a visual kind of thing. We look at all of the probabilities. For a table, it's a visual thing. We look at all of our probabilities, and they are between 0 and 1. Check. Now, if they gave us a probability distribution for this as a function and not a table, we would have to then evaluate each of those possible values for the random variable in that function to see if it works out that it gives us the probability between 0 and 1. So, yay, this is a probability distribution. It is a discrete random variable because it only has 3 possible outcomes. Awesome. Here's what the histogram will look like. Now, if we look back to the table, I'm going to flip back, okay, we can see all the information that we need is right here in this table. And the histogram is just essentially the exact same thing as like a relative frequency histogram, except instead of being percents on the vertical column or the vertical axis, it's probability. Okay, that's it. That's all it is. Now we're done with that. So here's a potential probability formula, right, an equation for this exact same situation. And we can see that it restricts us. It says that P of x equals 1 over the quantity 2 times 2 minus x factorial times x factorial, where x can be 0, 1, or 2. So we can see here how this function, P of x, is infinite. It will go on forever. I mean, factorial doesn't, it's kind of weird if you try and talk about, 1.5 factorial. We don't really do that. It's kind of not a good math thing. But you could have 0, 1, 2, 3, 4, 5, all the way up to infinitely far, but we just restrict it from 0 to 2 so that it maintains that it is a probability distribution. And so we can see that when we plug in 0, 1, and 2, we get the values we're looking for. Now, here's something where we had a group of managers were interviewed and asked what are some common mistakes that interviewees make. Is this table a probability distribution? Take a minute, think about it, pause the video, see if you can identify, is this table a probability distribution? Yes or no, and why? All right, so now you've had time to do that, let's look. No, it is absolutely not a probability distribution. First of all, our random variable x is not a numerical random variable. Second of all, the table's values do not sum to 1. Matter of fact, we have 0.5, 0.44, 0.33, 0.3 sums up to 1.57. So since just one of these rules was broken, one of those 3 restrictions for probability distribution, this is not a probability distribution. It doesn't matter if one of the rules is broken or all of the rules are broken. If any rule is broken, it's automatically not a probability distribution. To be a probability distribution, you have to satisfy all 3 conditions. So let's talk about the parameters of a probability distribution. So since probability distributions are descriptive of the population, they're not just a random sample, they're a population, we're dealing with the parameters of this and not the statistics of this, right? Because population parameter, sample statistic. You guys remember from chapter 1? I know you do. So we're going to talk about finding the mean, standard deviation, and variance. And variance is, again, one of those things that we're mentioning but not going to ever use. So if we have a discrete probability distribution, finding the mean and standard deviation is pretty simple. It's not crazy difficult, but it can be very complicated and tedious. Okay, the mean, mu, for probability distribution is simply the sum of the random variable values times their respective probabilities. So that's what this is saying right here. Take the value of the random variable, multiply by its probability. Okay. The standard deviation is a lot muckier. So it is the sum of the value squared of the random variable times its probability. And then once we've added all those together, we subtract this mean squared, and then we take the square root of all that. Okay. You're looking at that going like, oh my God, when is he going to make me do this by hand? The answer is I probably will never. Okay. To get this variance, we simply just square the standard deviation. Remember, standard variance is simply defined to be the square of the standard deviation. Now, there's one other thing that we get with with a probability distribution, and more importantly, a random variable. We get something called an expected value. Okay, if we have a discrete random variable, the expected value is exactly the mean. So it's really nice. We don't have to do any extra work. Once we found the mean, we can get our expected value. And we're going to have some examples where we utilize expected value here in a little bit, and we talk about kind of how it works and what it's used for. So back to our tossing 2 coins. Let's find the mean and standard deviation. Okay, we've got a nice little table. So we can see that the left 2 columns, for the most part, are just our probability distribution. The right 2 columns are going to help us out finding the mean and standard deviation. So if I multiply the the random variable value times its probability, so I take 0 times 0.25 gives me 0. 1 times 0.5 gives me 0.5, and 2 times 0.25 gives me 0.5. So those are my 3 values of x times p of x. Now if I total those up, I get 1. And that is our mean. Okay. So we come back over here. Now this last column is the probability value squared times its probability. So 0 squared is 0, 0 times 0.25 is 0, 1 squared is 1 times 0.25 is 0.5, or sorry, 0.5, not 0.25. And 2 squared is 4, 4 times 0.25 is 1. So we add those together, we get 1.5. Awesome, right? So very simply, our mean is 1. We're done. Our standard deviation, okay, we have the sum of the the random variable squared times its probability gave us 1.5. So that's this whole first piece here. We subtract off the mean squared, and 1 squared is still just 1, so we subtract 1. We get 0.5, so then the square root of 0.5 is 0.71. Now, you may wonder, why did I go 1 decimal or 2 decimal places? We only have a random variable goes 1 decimal place. Well, this is just the calculation part. I haven't stated my answer yet. So here we can see, now when I state my answer, when tossed a coin, the mean number of heads is 1.0, and standard deviation is 0.7. So, since our random variable is in whole values, our mean and standard deviation would go one place further, as the standard rule says. And so instead of being 0.71, which I just have here for the calculation purposes, it would be 0.7. Okay. This also tells me the expected value of this is 1. And so what that means is that if I repeat this procedure over and over and over and over again, in other words, I flip 2 coins and record the number of heads I get. If I do that over and over and over and over again, I would expect the average number of heads I got in those repeated procedures to be close to 1 over a long period of time. That is my expected value. Now, range rule of thumb. We've talked about this kind of idea before, being 2 standard deviations away from the mean. It still applies. Something is significantly low if it's below the mean minus 2 standard deviations. It's significantly high if it's above the mean plus 2 standard deviations. Now, if it's in between, this says value is not significant. And I don't really like that term because it makes it seem like they're not important. But that's not the case. That just means that they are not significantly high nor significantly low. So that is anything but that's between the mean minus 2 standard deviations and the mean plus 2 standard deviations. Okay. So, looking at our example of flipping 2 heads, okay, if we want to use the range rule of thumb to determine whether 2 heads is a significantly high number of heads, we just simply add 2 standard deviations to the mean. And when we do that, we get 2.4. So any number of heads that's 2.4 or above would be a significantly high number of heads given 2 coin flips. Now, we obviously know from what I just said that's impossible. So 2 heads is not significantly high because it's not above or touching 2.4. Now, this is a really important idea here. This is something that we're going to use a lot because this is something that will help us to kind of identify if something is unusually high or if it's just happened by random chance. Okay, so if we have X successes among N trials, then this is significantly high if the probability of getting that many successes or more is less than 0.05. Okay, and remember this 0.05, just like before we talked about, we had kind of mentioned this a little bit. 0.05 is an arbitrary number. It's pretty kind of a standardized, general thing, but depending on what scenario you were in, you may want to increase it or decrease it depending on what you're looking for, if you want to be more or less rigid. So very simply put, the probability of X successes or more, so that means we're including X in there, has to be less than or equal to 0.05 for something to be significantly high. Significantly low is just the exact same thing, but instead of X or more, it's X or fewer. So getting less than or equal to X successes in our trials. So this is where this comes into play. If we have some sort of given assumption on something and then the probability of an outcome is either very small, or the probability of an outcome is very small. In other words, we're falling into one of these 2 categories, okay, then it is fair to assume that our assumption is not correct, or is probably not correct. And so what's happening here, what we're talking about doing is these significantly low or significantly high ideas are referencing this thought of something being a result occurring from just random chance versus it occurring because something that we thought was happening is actually not happening, or vice versa. Some false assumption being taken place. We're going to see later on in this lesson, there's going to be something where we have a false assumption, and it causes the probability to be very low. And we'll talk about that there and kind of how we interpret that in the context of a problem. Okay. Expected value is just the mean. We already talked about this. So let's talk about betting. So how do you want to be a smarter bettor? So to think about this, we think about doing one of two things. Okay, so let's say you have $5 to bet at a casino. Which is the better bet? At roulette, okay, betting $5 that the number 7 comes up, or in craps, betting that the pass line happens. Now, if you aren't familiar with roulette or craps, it doesn't matter. Just understand that getting a 7 is a winner, betting the pass line, you've got a winner or a loser. I've found the probabilities for you. That's not something I'm expecting you to do in this part. Okay. So what we want to do to figure out which one's a better bet, long term more so than immediate term, is to find their expected values. So if you bet $5 on the number 7 in roulette, since there's 38 spaces, you have a probability of 37 over 38 of losing. So you would lose $5. However, you have a probability of 1 over 38 of winning. And if you win, the prize is $180. However, you bet $5 already, so you kind of started out with getting rid of that $5. And so you have a net gain of $175. So to find our expected values, we take our random variable value, which in this problem here, the random variable we're concerned with is the amount of money we make. So if I lose, that means the amount of money I make is negative $5. Ooh. There we go. So for roulette, if I lose, I make negative $5, and that happens with a probability of 37 out of 38. And so the random variable times its probability gives me negative 4.868421. Now if I win $175, but that only happens with a probability of 1 out of 38. So if I multiply these two together, I get 4.605. And by adding them up to find our mean or our expected value, we get negative 0.26. Or in other words, our expected value is to lose 26 cents. Okay, I'm going to go back one slide. Now, if we bet $5 on the pass line in craps, the probability of losing, which there's a lot of ways to lose, a lot of ways to win in craps, and that's why I've calculated these probabilities for you, and that's why you're like 495, what? It's the way these are accurate. So if we lose $5, that has a probability of 251 over 495. However, if we win, we get $10. But again, we've already bet our $5, so we have a net gain of $5. And that happens with a probability of 244 over 495. Now, you may be thinking, like, okay, well, which is a better game? Well, this one here, like, it's almost a 50-50 shot of winning. However, with roulette, you won significantly more. And so that's something you have to take into account as well. So now if we look at the craps game, if we lose $5, or random variable value is negative 5. That happens with the probability of 251 over 495. And if we win $5, and that happens with the probability of 244 over 495. So if we multiply these together and add them up to give us our mean or our expected value, we get negative $0.07 or negative 7 cents. And so what do these mean? Okay, so for roulette, we had negative 26 cents. For craps, we had negative 7 cents. There's no change happening in any of these, right? You don't see a casino doling out quarters and pennies. So how is an expected value negative 26 cents when my payouts were $5, or I lost $5 or I made $175? And what that is it's saying that if you do this same bet over and over again for a large enough amount of times, the average that you either made or lost would average out to approximately negative 26 cents and negative 7 cents, respectively. Okay? And so what that means is if you bet 7 on the craps table 1,000 times, you're going to lose a lot, but you might win once or twice. And in the end, your average for each kind of round would be about negative 26 cents. Okay? So to be a better bettor, as the cheesy title states, we are looking for the least risk, so the most positive value, or the closest to a positive value in this case. And that would be the -7 cent crap bet. So betting craps, betting the pass line at craps, is a better bet in the long run if you are going to do this over and over and over again. Now, binomial probability distribution. So that's it for probability distributions. Now we're going to specify into a certain type of probability distribution, and it's a very important one for the binomial probability distribution. Okay. And key focus, you can do that. So a binomial probability distribution results from a procedure that meets these 4 requirements. Just like a probability distribution had 3 requirements, a binomial probability distribution must satisfy these 4 conditions for the procedure to work. So the procedure has a fixed number of trials. A trial is a single observation. So flipping a coin twice, that would have a fixed number of trials of 2, with each flip of the coin being a single trial. Okay. The trials must be independent. So that means that if we're drawing a card from a deck of cards, it has to have replacement. We cannot be without replacement, because then those 2 events are not independent, and this would not be met. The third condition is that there has to be 2 outcomes, and 2 outcomes only. And we typically refer to these as success or failure. Now, there's a big note I'm going to bring up later. I'm going to bring it up now as well. Success does not mean the normal thing that we mean success by. So success is not necessarily a good thing. Success is just whatever the outcome that we are looking for. And the last condition is that the probability of a success remains the same in all trials. And there are situations where the probability of success would not remain the same in all trials, even though all trials are independent. And that would be a fairly rare exception, but an exception nonetheless. So, speaking of these successes and failures, we say that the probability of success, we let that be represented by this lowercase p. So lowercase p is the probability of success, where the probability of failure is 1 minus p, because they're complements of each other, and we let lowercase q represent the probability of a failure. Okay, so these are the 2 probabilities that we're dealing with this problem. That is trial to trial fixed values. Okay, n is the fixed number of trials. So whatever we have going on, say I'm flipping a coin 5 times, that could potentially be a binomial procedure resulting in a binomial random variable. So a binomial random variable is simply a random variable that occurs from a process that satisfies the conditions of a binomial probability distribution. So if we have a binomial probability distribution, the random variable that it is referencing is a binomial random variable. Pretty easy. A couple more things. So x is a specific number of successes in the n trials that we've dealt with. So it can be any number from 0 all the way up to n. So when we link back to flipping 2 coins, you can start to see, hey, that was a binomial process. Each time we always had 2 trials. That was fixed, never changed. Let me go back. The trials are independent. If I flip a head on one coin, it doesn't affect what happens on the other coin. Or if I had one coin flipping it twice, it's still the same thing. It doesn't affect it. There's only 2 things. We either get ahead or we don't, because that's what we're looking for, right? Even though with coins you get heads or tails, we can even think about this with a die roll. If I'm looking for a 2, either you get a 2 or you don't get a 2. Okay. And back to the coins now. The probability of success remains the same in all trials. So in other words, every time you flip the coin, you have a probability of 0.5 of landing on heads. Ignore any landing on its edge or anything like that. So P and Q, probability of success in one trial. Q, probability of failure in one trial. P of x is the probability of getting exactly x successes among the n trials. And we'll deal with some problems that kind of change that as we go. So again, this is something that kind of talking about like I said, the word success is not used in its grammatical English sense of success being good. A success could be getting in a car crash, right? If the problem we're looking at is people driving their car, they either get in a car crash or they don't, right? A success could be getting in a car crash. And so we need to kind of dispel any notion of success being the good thing. It is simply the thing that we are looking for. Now, it's really important that you are matching your X and your P. In other words, the number of times something happens corresponds to the probability of success, and that you don't kind of mix those up. It's not something I see very often, but we just want to make sure we make a point of not doing it. So let's look at an example. Twitter is a pretty fun little thing if you like social media. But if a random adult is selected with replacement, we say, so that is key right there. There's a 0.85 probability that this person knows what Twitter is. Okay. So if we want to find the probability that exactly 3 of 5 randomly selected adults know what Twitter is, we can use binomial random variables or binomial probability distributions to help us find this. So there's 2 questions. Does this procedure result in a binomial distribution? And if so, find the values n, x, p, and q, and then find the probability. So for this to satisfy our conditions, we just need to go through. Well, we're asking 5 people, so that's our 5 different trials. Because we have this with replacement up here, right? A random adult is randomly when an adult is randomly selected with replacement. That gives us that each trial is independent. We're not removing one adult from the population, and so our probability changes. Now, with that said, whenever we deal with a large quantity like population, it is safe to assume that in a sample of people that is still independent, even though we don't replace them, right? Because we're not randomly going to ask the same person again. And so if you are just pulling people on the street and asking them a question, it's safe to assume that those results are independent of each other. So here, independent, check. Step 3, or condition 3, each of those 5 trials, they either knew what Twitter is or they don't. 2 outcomes. And lastly, every adult has a probability of 0.85 that they know what Twitter is, and it's the same for all adults, so it works. It says the probability of success is fixed for all trials. So that tells us, yay, this is a binomial probability distribution. Now, part B. What are our variables? Well, n is the number of trials we have, which, since we're asking 5 people, n is 5. X is the number of successes we want. Since we want to know the probability that exactly 3 people know what Twitter is, x is 3. Now, since we were told that 0.85, that the probability that any one person knows what Twitter is 0.85, that tells us that p equals 0.85. Since it's a complement, means that q must be 0.15. Now, this is what we're talking about when we're talking about mixing things up, right? We don't want to accidentally use 0.85 for the probability of failure when it's actually the probability of success. So we have to make sure that we are keeping that straight. Now, it's very important to make sure that we do that. I just said all this. 5%, this is just, people, even if we don't replace them, that's independent. Now, there's 2 ways we're going to talk about to calculate this probability. 1, using our formula. It's a lovely, beautiful formula, and it works so well. Okay, so the probability of x, so in other words, the probability that we get exactly x successes in n trials is equal to n factorial divided by the quantity x minus n factorial times x factorial times p to the x times q to the n minus x. Now, there's a lot going on here, and you might be going like, what in the world is happening? It's really a simple idea. Okay, so let's break it down. This first piece here, this n factorial over x minus n factorial times x factorial. If you think back to counting, this is the combinations formula. This is n choose x. We start with n things, we want to choose x of them. And so what's kind of happening here, this idea is that if I have 5 trials and I want 3 successes, I could get 3 successes in the first 3, right? I could have success, 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 success. Wow, that was a little tongue twister for me. Followed by 2 failures. But I could have success, success, failure, success, failure. And so if I think about the number of ways to choose 3 of those 5 things to be my successes, the remaining 2 have to be my failures, so those just fall into place. And that is the number of ways that I can have 3 successes exactly in 5 trials. So that's what this first thing tells me. The next thing tells me the probability of success, so that's our little p, and that's raised to the xth power. So this is just using the multiplication rule. Let's say we have success, 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 failure, failure. To find the probability of that, that's just simply the multiplication rule. So we're looking at this first, then this, then this. Since they're all independent, we just multiply their probabilities. So the probability of getting a success is p. So then the probability we get success, success, success is p times p times p. In other words, p to the x. And then we have to get the remaining failures, which has a probability of failure is q. So we have times q times q. And so when this boils down, for our problem here, now is where I'm going to jump ship. Okay, so for our problem here, let me grab it a little bigger for you. So what we have to do, so this is using a TI-84 Plus Silver Edition. Depending on your calculator, you may have more or less things. I'm going to do this kind of in an 83-ish way. If you have a newer calculator, you can use these fraction buttons. You get a fraction, type these in really easy. I'm not going to do that. So we have 5 trials. Go back to math, probability, option 4. Okay, we need to divide that. Now I'm going to use 2 parentheses because that first parenthesis is the 5 minus 3. And then instead of scrolling down, notice the number 4 there, so I can just hit number 4. It gives me a factorial. Times 3. So this right here is that first piece. So what this means that in 5 trials, there's 10 different ways to get 3 successes. So there are 10 different ways to get 10 different orders that those 3 successes come in. So either 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5, right? We're not going to list them all out, but that's 10 of those different things. Now for each one of those, we have the probability of success, which is 0.85, times itself 3 times. And so that's just simply cubed. Okay, but we also have 2 failures every time. So we also multiply that by the probability of failure, and that happens twice. And we get 0.1381788125. So let's say 0.1382. Okay. So back to our slideshow. So we get all of this, and we get 0.138, rounded to 3 significant, or three digits. So this tells me the probability that if I pull 3 people, or if I pull 5 people, that exactly 3 of them knows what Twitter is, that is simply 1.138. Now, that's not at least 3, right? So that's not saying 3, 4, or 5 people know. It's saying exactly 3 of those people know. Using technology, we just did that as well, so ta-da, but let's do it again. So, between 1974 and 2011, there were 460 NFL football games that were decided in overtime. Now, for those of you who watch football, you know that overtime rules have changed in recent years, so 2011 is prior to that change. So this is all the old system. For those of you who are unfamiliar with football, the overtime rules are very simple. They flipped a coin. The team that won the coin toss got to choose if they wanted the ball or they wanted to kick the ball away. And then in overtime, the first team to score any points wins the game automatically. So getting the ball first was perceived as an advantage. Now, we are going to look at that statistically speaking right now. So between 1974 and 2011, there were 460 overtime games, with 252 of them being won by the team that won the overtime coin toss, because you always chose to get the ball if you won the overtime coin toss. Now, what we want to do is we want to figure out, was this significantly high? Remember, significantly high. In other words, it is kind of within that probabilistic range. In other words, getting 252 wins or more in 460 games, that probability would have to be less than or equal to 0.05 for us to be able to say this is significantly high. Now, we're going to talk more about this as we go through and kind of some of the fun caveats with this and kind of how we interpret and use our results. So, we don't want to do this by hand. So 460 trials. If we assume that it's a fair result, in other words, that overtime is just as fair as any other part of the game, right? We're not talking about, we're minusing, team talent and things like that. We're just saying 50-50 shot of winning overtime, assuming teams are somewhat equally matched. There's too many real variables if we wanted to kind of really dive into this truly, but we're going to assume teams are evenly matched. So the formula here is pretty simple, except the problem is I would have to apply it 209 times, because to figure out if something is significantly high, we need to find the probability of getting 252 wins or more. That would mean I would have to use that probability formula, binomial probability formula, for 252, 253, 254, 255, 256, all the way up to 460. That is 209 different calculations. That is way too much. Even if I had all those calculations listed in a table, I don't want to add them together. So we're going to use our calculator to do this. Okay. Now, there's two different calculator functions. At this time, if you have not yet looked at that website on how to do this in your calculator, pause and go do that real quick. Okay. Let's jump into our calculator and show you guys how to do this. So what we're going to actually do real quick, I'm going to go back to this one and show you this using our calculator, and then we'll do our overtime rules. So exit out of that, bring our calculator up. Okay. To get to the probability distributions that we're going to be using, right? We are talking about these distributions, so we are going to go to this DISTR for distributions. So you're just going to hit second, and then this bars button to take us into the distributions. Now, don't worry about draw. We don't need that. That's not what we're going to do. We want distributions. There's a lot of distributions that our calculator has. There's normal PDF, normal CDF, inverse norm, inverse T, TPDF, TCDF, chi-squared PDF, chi-squared CDF, all sorts of different things. Don't worry about it. Right? If we scroll all the way down, or if we just jump up, there are 7, or it goes all the way to F. So 1 through 0, then A, B, C, D, E, F. Okay. But we want binomial. So that is our option A or B. Or if you're in some other calculators, it may be options 0 and A. Depends on which version you have. I believe the 83 is a 0 and A options. But what you're looking for is binom PDF and binom CDF. Now these two things calculate probabilities very differently. The binom PDF is the binomial point distribution function. It is looking at the probability of a single point value. Okay, so if we go up to that, so this is what we would use for that first problem, that Twitter problem, okay? Because we're looking at getting exactly 3 successes. So here, depending on which screen you have, you're either gonna have this menu or you're gonna have, it just pops up on your screen, and I'll get right there in just a minute, okay? If you have this menu, it's really nice, it's laid out for you. So we had 5 trials, okay? The probability of success in the Twitter problem was 0.85. And we were looking at an X value. We wanted an X value of 3 because we wanted exactly 3 successes in these 5 trials. So we do that, paste, and it gives us this. Now, if you didn't get the menu, when you clicked binom PDF out of the distributions, it should look like this on your home screen. And you're just going to type the exact same information in, and you're just going to do 5, the number of trials, comma, right here next to the parentheses, comma, probability of success, 0.85, comma, the number of trials or the number of successes we want. Close your parentheses, and that's it. That's definitely something that if you don't have the menu, you need to write that down so you don't end up on the test going like, oh man, what is it? And hunting through your notes and doing a bunch of crazy stuff. Having that written down on like a 3x5 card is really nice and helpful. So hit enter. We get 0.138178125, or that 0.138 that we're looking for. Okay. Now, real quick. Binomial CDF is a continuum of values that it calculates. What it calculates exactly is it calculates the probability that x, our random variable, is less than or equal to some number. Okay? That is what CDF does. Always. You can't change that. If you have some really new calculators, there's some that you can do some tweaks with it, but for the most part, don't tweak it and just stick with this. So if we want to know the probability of getting 252 wins or more, what we have to do for binomial CDF, is we have to actually do the complement. So the opposite of getting 252 wins or more is getting 250 wins or less. And that's what this is right here. This is saying that x is c, that's the equals part, or less. And so we can use the binom CDF using 460 trials. And remember, in this problem, we're assuming that it's a fair outcome. So it's 0.5 is our probability of success. And we want 251 successes. Okay. Now, to do that in our calculator, we just go second and back into the vars to get to our distributions. We'll go back to our distributions. We go up to binom CDF. Choose that one. Depending on which version you have, you're gonna do it in the same order. It's gonna be trials, then the probability of success, and then the X value you're looking for, the value you're looking for. So here we have 460 trials, probability of success is 0.5, and we want 251 or fewer trials or successes. And so we do that. Tell it to paste it. And we hit enter. So what this is saying is the probability that we get 251 wins or fewer in 460 games, if the overtime rules are fair, that probability would be 0.9776. Okay. Let's jump out of this, back into here. Now, since that's a complement of what we were looking for, because what we wanted to find is the probability of getting 252 or more. We need to use those complement rules, which says that I can take 1 minus the probability of the complement to find the probability I'm looking for. So I do 1 minus 0.97757, and I get 0.02243. Okay? 0.02243. Now, what that tells me is that the probability of getting 252 wins or more is less than or equal to 0.05. So what that means is that that is an unusually or significantly high result. So what that tells us is if we would have gotten 250, something that, let's say 248 wins, something where this probability here wasn't less than or equal to 0.05. We would say, well, that just is some random chance. And we can explain that away by saying, well, sometimes teams are better than others and they get it overtime and the better team takes the head. And there's lots of different things. You could say that was just a random occurrence of kind of getting more than the middle. Now, here, because this is an unusually or significantly high value, we would say that one of our assumptions is wrong. Since the main assumption we made was that overtime rules are fair, that assumption is wrong. So the traditional or the old way of doing overtime in the NFL was not a fair method to establish a winner, but it favored whoever won the coin toss. So that's how we can kind of use these unusually high, unusually low, significantly low, significantly high values. We just simply kind of look at them, and if something is unusually high or unusually low, that means that most likely one of our assumptions was wrong. If the result isn't unusually high or unusually low, even if we go like, that kind of looks a little high, that just means that it was just random chance, right? If you flip a coin 10 times, we know the expected value is 5 heads, 5 tails. But, I mean, I've flipped coins and gotten 6, 7, 8 heads even. That doesn't mean that that coin is broken or that coin is off. That just means it was randomly chance that I got a couple more than normal, okay? Now, you remember mean and standard deviation, those formulas, right? Especially standard deviation, that was a gross one. For a binomial random variable, it's really nice. The mean is simply the number of trials times the probability of success. The standard deviation is the square root of the number of trials times the probability of success times the probability of failure. Right? Variance is just the square of that, so it's just n times p times q. So the mean is simply n times p, and the standard deviation is the square root of n times p times q. That's all you have to do. So we don't have to go crazy and do anything insane. We just have to simply multiply these nice, easy numbers together. Okay? So in 460 overtime games, if we make our assumption that overtime coin toss is fair, so in other words, probability of success is 0.5, probability of failure is 0.5, okay, we can find our mean and standard deviation. The mean, n times p, is simply 460 times 0.5, which is 230 games. So that means that the expected value, if the overtime rules are fair, in 460 games, it is expected that 230 of them would be won by whoever won the coin toss. And so what I mean by this is if we were able to simulate 460 games, all being overtime games, over and over and over and over again. So those 460 games creates one kind of occurrence. And if we do that over and over again, tons and tons of times, the number of successes, the number of people who won the coin toss and won the game, those would be kind of our data points. And the average of those data points would be 230, or close to. And now the standard deviation is the square root of n times p times q, square root of 460 times 0.5 times 0.5, which is 10.7. Okay. Again, our data values are whole number wins, so we're going one decimal place beyond for our mean and standard deviation. Check those out. Make sure you guys agree. All right. So again, a significantly high result is if the probability of getting X or more successes is less than or equal to 0.05. Significantly low result would be getting the probability of X or fewer, meaning less than or equal to 0.05. Okay, notice both of these, the probabilities are less than or equal to 0.05. The X or more is simply talking about if it's high, we want to know what's the probability of getting that number or more. If we think it's low, we want to know what's the probability of getting that number or fewer. Okay, that's it. That's the end of this lesson. So take some time, absorb this, watch this again, whatever you need to do. Practice the calculator. Get onto this homework, okay? The biggest thing here to take away is that this is really simple because you're just identifying your N, your P, your Q, and whatever X you need. And then you just have to figure out, do I need to use PDF because I want to find a single exact X value, like the Twitter problem? Or am I using CDF because I want to find a kind of continuum or a bunch of different values like we did in the football problem? So that's it for me, guys. I hope you guys learned something here. Get working on the homework. Make sure you guys get your discussion problems done, and I'll see you later.